In this video, we're going to begin discussing the cross product of two vectors. And we're going to start this discussion by looking at a motivating question that we will need to answer in subsequent parts of this course. And that question is the following. So if we're given non-zero vectors u and v in R3, what is a vector that is orthogonal to both u and v? So in other words, we want to find a vector that is mutually orthogonal to two given vectors. Now, we know how to determine if two vectors are orthogonal. So if we let C be such a vector, so a vector that is orthogonal to both u and v, right, then we know that u dot c, the dot product of u and c, must be the zero scalar, and also that v dot c must equal the zero scalar, right? Because two vectors that are orthogonal have a dot product of zero. Well, we can write out each of these dot products as an equation without the dot product, without the vectors, by just thinking of u, v, and c in component form. And so u, v, and c, I'm going to denote the components by subscripts of 1, 2, and 3 like we've been doing. So u dot c is going to be u1, c1 plus u2, c2 plus u3, c3, and we want that equal to 0. And v dot c is going to be v1, c1 plus v2, c2 plus v3, c3. And so we have this system of equations where we think of c1, c2, and c3 as our variables, and u1, u2, u3, v1, v2, v3 as just our coefficients. And then we can solve this system. Right? This is just algebra. So we're going to skip the solution part. But if we solve it, we find the following solution. We find that C1 has to be U2 V3 minus U3 V2. C2 will be U3 V1 minus U1 V3. And C3 will be U1 V2 minus U2 V1. Right? So just by algebra solving this system of equations, we find that the vector C that we want that is orthogonal to both must have these particular coordinates. And so these three coordinates C1, C2, C3 are going to be our definition for the cross product. Okay. So for our definition, if we're given U with in component form U1, U2, U3, and a vector V in component form V1, V2, V3. The cross product which we'll denote with the old school multiplication symbol, is defined to be U cross V equals and then it's in component form, is the vector that we just wrote down. So u2 v3 minus u3 v2, u3 v1 minus u1 v3, and u1 v2 minus u2 v1. Okay, so this is the cross product of the two vectors u and v in component form. And so this vector will be mutually orthogonal to both u and v. Now, this is not the best formula to use to actually compute the cross product. If I had specific vectors u and v, in order to use this, we'd have to memorize this formula. And so we are going to come up with a more efficient way of computing the cross product in a moment. But before we do that, we should make a couple observations about this cross product, and specifically about how it differs from the other kind of product we've talked about, the dot product. So the first thing to observe is that u cross v is always a vector. Right? There's no way to get anything other than a vector when we take the cross product, whereas u dot v is always a scalar. So these two different products are very different operations. Not only are they defined differently, but they produce very different objects. One produces a number, and the other produces a vector. The other thing to point out is, because the cross product is a vector which is orthogonal to both u and v, the cross product u cross v only makes sense in R3. So we cannot take the cross product of two vectors in R2. It just doesn't make any kind of sense. You can see that even just by looking at the formula. There's a u3 and a v3 involved here, and in R2 those components don't exist, so we wouldn't be able to use this definition. But even then, we wouldn't be able to come up with a comparable definition in R2 either, because the result of the cross product is something that just doesn't exist in that world. So in order to compute u cross v efficiently, we're going to consider determinants of matrices. Now, some of you might know how to do this, but I'm again going to take the approach that you know nothing about matrices and nothing about determinants. So if you do, that's great, but if you don't, that's fine just as well. So we're going to start off with a 2x2 matrix. Right? So a matrix is just a rectangular array of numbers. So a 2x2 matrix is a matrix with 2 columns and 2 rows, like A, B, C, D here. And the vertical bars represent that we're going to take the determinant of that matrix. And the determinant of the matrix A, B, C, D is the number AD minus BC. So what we will always do in the 2x2 case is we will multiply the main diagonal elements, the top left and the bottom right, and then we will multiply the other two, the top right and the bottom left, and then subtract those products, the AD, starting with AD and subtracting BC. All right, so this is how we're going to find the determinant of a 2x2 matrix. Right? So if I had a matrix, something like 1, -3, 2, and 5, the determinant of this matrix would be the number I get by starting by multiplying 1 and 5 together, subtracting from that the product -3 times 2. So this would be 5 plus 6, which is 11. So the determinant of the matrix 1, -3, 2, 5 would be 11. Right now, to compute the cross product, we need to compute 3 by 3 determinants. Right? So I need to compute a determinant of the following matrix, something of the form ABC, DEF, and GHI. Now I know E and I have mathematical meanings elsewhere. These are just, in this example, E and I are just real numbers. And so the way that we're going to look at this determinant is in the following way. We're going to go across the top row. So we're going to start with the element A. And what we're going to do is we're going to mentally erase the column and row that contain A. So I'm going to just use this dotted line because I don't want to erase it because we're going to need the numbers later. But I want to mentally erase, in this case, the column below A, the D and the G, and then the row containing A, which is B and C. And when we do that, what's left is a 2 by 2 matrix, EFHI. And so to get started with this determinant of the 3 by 3 matrix, we're going to take the number A, that element in the top left corner, and multiply it by the 2 by 2 determinant EFHI. Right, so this is our first step, is the top left element multiplied by the remaining 2 by 2 matrix when we erase that column and row that contain that element. Right, now we're going to move over to the next element in the top row, and that's B. And we're going to kind of approach it the same way. We're going to get rid of the things that are in the same row and column as B. And when we do that, we're left with not a 2 by 2 matrix, but we're left with 2 columns, DG on the left, FI on the right. But if we push them together, we would get a 2 by 2 matrix. Right? So what I'm going to do is I'm going to subtract B times the 2 by 2 matrix that's indicated in blue here, which would be DFGI. Right? And then the last step here, we've already done the A, the B. Now we're going to look at the C. We're going to mentally erase everything above and beside the C. And so we're left with this 2 by 2 matrix here. So we're going to add to this C times the 2 by 2 determinant DEGH. Right. So we've broken up this 3 by 3 determinant into a sum and difference of 3 2 by 2 determinants, which we know how to do from above. The one thing I really want to point out here is that this term here, the middle term with B, is negative, right? With the A and the C term, right, the C is an addition, and there's an implicit positive sign in front of that A. But it does have this alternating pattern where we take the first term and we add it, the second term is subtracted, the third term is added. So that is probably the number one computational mistake with cross products, is to add all 3 of these together instead of subtracting the B term. All right, so let's look at an example of a 3 by 3 determinant. So let's say I wanted to compute 2, 1, -1, 3, 0, 2, and -1, -1, 2. All right, and I want to compute this 3 by 3 determinant. All right. Well, we're going to start. We have the top left corner there is a 2. And I want to multiply it by the determinant I get by removing the first column and first row, which would be 0, 2, -1, 2. The next term I know I'm going to subtract, and this is going to be the term with 1. So it's going to be -1 times the determinant I get by removing the top row and the middle column. So if I do that, I have 3, 2, -1, and 2 left. And then we're going to add to that the third term, which will have a -1. And then the 2 by 2 determinant, 3, 0, -1, -1. So that should go right there after the -1, but sort of ran out of space. So this is our determinant. These are our 2 by 2 determinants now we have to compute. Right? So we have 2 times this 2 by 2 determinant. So that's going to be 0 times 2 minus 2 times -1 minus 1 times 3 times 2 minus 2 times -1 plus -1 times 3 times -1 times 0 times -1. Right? And so we just compute what all of this is. So this looks like 2 times 2. Right? That's going to be 0 plus 2 in parentheses, minus 1 times the 6 plus 2. That would be 8. So 1 times 8. And then I'm going to go ahead and write this one as -1 instead of plus -1. And that'll be -3. So we get 4 minus 8 plus 3, right, which is -1. So the determinant of this matrix is -1. Right, well, this is all fine and good, but you're probably wondering how this relates to cross products. So what we're going to do is we're going to write the vectors u and v not in component form, but we're going to write them with those standard basis vectors I, j, and k. So I'm going to write u as u1i plus u2j plus u3k. And similarly for v, I'm going to write v as v1i plus v2j plus v3k. So if we go back to that definition of u cross v that we wrote down earlier, and we write it in using the standard basis vectors instead of in component form, we get u2v3 minus u3v2 times vector I. And then I'm going to write this, and I'm going to factor out a negative from that second component, and I'm going to make it negative u1v3 minus u3v1 times j. All right, now if you look back at the old definition, we had u3v1 minus u1v3. And so if I factor out a negative, I get what I have written here now. And then I'm going to add to this the third component, which is u1v2 minus u2v1 times vector k. All right, so this is just our notation, our component form of u cross v written in standard basis form. And now if you look at each of these three real numbers, these three components, and now that we've talked about determinants of 2 by 2 matrices, you might be able to see this connection that these look a lot like determinants of 2 by 2 matrices. There it's a product of two numbers minus a product of another two numbers. And so it turns out that we can reconstruct some 2 by 2 matrices for which these are the determinants. So for the first one here, we could write the matrix u2, u3 as one row and v2, v3 as another row. And you can quite easily check that that will be u2, v3 minus u3, v2. We can subtract from that the determinant of the matrix u1, u3 over v1, v2, or v1, v3 rather. And the third one here is the determinant of u1, u2 over v1, v2. So I've just reconstructed some 2 by 2 matrices from these little numbers that we had in front of I, j, and k. And now if you look at this, this looks a heck of a lot like the determinant of a 3 by 3 matrix. I have a single thing, I, j, or k, multiplied by a 2 by 2 determinant, and the first is added, the second is subtracted, and the third is added. And it turns out that this expression is the determinant of the following matrix. So the first row will consist of our unit vectors I, j, and k. Our second row will consist of the components of vector u, which are u1, u2, and u3. And the third row will be the corresponding components of v, v1, v2, and v3. Okay. So it turns out that if we just kind of look at the beginning and end of this chain, we have a kind of an efficient way of computing u cross v. We're going to form a 3x3 matrix with the unit vectors I, j, and k across the top, the vectors u and v written horizontally as rows 2 and 3, and then we take the determinant of that matrix. So let's take a look at an example. So let's say we want to compute -2, 5, 1 crossed with 1, 3, -1. All right, so using the determinant formula that we just derived, we need to find the determinant of the following 3x3 matrix. So we'll have I, j, and k across the top. Our second row will be the entries of the first vector, -2, 5, and 1. And the last row will be the entries of our second vector, 1, 3, -1. All right, so when we go to compute this 3x3 determinant, we're going to go right across the top row. So we'll start with I, and we'll want to multiply I by the determinant of the remaining 2x2 matrix, which will be 5, 1, 3, -1. That'll be times I. Remember, the second term here is subtracted. So with the j, we remove the first row and second column. So we're left with -2, 1, 1, -1. This is j. And then for k, we remove the first row and third column. So we have -2, 5, 1, and 3. All of that times k. So now we compute these 2x2 determinants. So this first one here is going to be -5 minus 3. So that's going to be -8i. Minus the second determinant, we have -2 times -1, which is +2, minus 1. So 2 minus 1 is 1. But that is a negative because of the negative from the determinant formula. And the last one here, we're going to have a determinant of -6 minus 5. So that's -11k. Right? And so if we want to put this back in component form, we can do so. We just read off the coefficients of I, j, and k, -8, -1, and -11. Right? So this is a vector which would be orthogonal to both -2, 5, 1 and 1, 3, -1. Right? You can easily check that. Take each of those two original vectors, take the dot product of them with -8, -1, and -11, and you will get 0. So if you want a little bit of a practice with this determinant process, in case you've never done it before, let me suggest you try the following two examples. Try to compute 1, 3, -1 cross -2, 5, 1. Now you might say, well, those are the same two vectors that we just computed the cross product of, and just in the different order, and almost certainly this will be the same answer that we just obtained, the -8, -1, -11. But you will be, if you think that is the case, you will be surprised by the answer that you get here. And also try looking at a cross product of a vector with itself. So maybe 1, 3, -1 cross 1, 3, -1. Okay. So, and again, maybe you don't have any idea what you'll get here, but you might be a little surprised. So these kind of illustrate a couple properties with the cross product. Again, how it differs from the dot product, in that in the dot product you could take in any order. In the for a cross product, we cannot. The order actually is going to matter, as you'll see when you try this first example and you compare it with the previous example that I just worked out. When we took a vector and we took a dot product of a vector with itself, we've got the magnitude of the vector squared. And here we're going to get something very different than that.